Great. Welcome everybody to lecture A.9. Last time we saw a first construction of a linear size IOP. We targeted a specific problem, which was something like arithmetic circuit satisfiability, and more precisely, it was a language, an NP-complete language called R1CS, rank 1 constraint satisfiability. The core of the construction was a univariate sum check, because we arithmetized the computation using univariate polynomials. This was ultimately with the goal of relying on using a code that has constant rate and constant relative distance, while at the same time giving us kind of flexibility in arithmetization and eventually also having an efficient proximity test, in that case, the Fry protocol. Now, just the fact that you construct an IOP with linear size for some NP-complete problem doesn't mean that it is not interested anymore to construct linear size IOPs for any other problem. In particular, there is one goal that we did not pay attention to last time, which was how do we make sure, can we make sure that the verifier has a running time that is much less than the computation itself? Okay, so that's what we're trying to do. What we're going to try to do today is to additionally achieve that goal. Okay, and for that, we're going to have to focus on machines rather than circuits for reasons that will become clear soon. So the focus of today is to obtain, as I said, linear size IOPs with sublinear time verification. And so this is the theorem that we proved. We proved that for a large enough field, that is smooth, the smoothness, we were using it for the low-degree test. The key properties that we achieved was the linear size and the logarithmic query complexity, but crucially, the running time was still linear in the problem size. But actually, this running time is in some sense optimal, because just reading the size of the circuit or the R1CS instance will cost you order of n time. So actually, that's an optimal running time for the verifier. Just like what you've seen, I think, yesterday, yesterday with Tom, with the PCP for NEXP, if you want the verifier to run in time that is sublinear in the computation needs to have some structure, so that the description of the computation is shorter than performing the computation itself. Okay, because the verifier at the end of the day needs to read the theorem that it wants to check. So in some sense, kind of the holy grail for that would be to consider the general class of non-deterministic machine computations, that is class n time t, right? And it would be wonderful to have a statement such as every language in n time t has an IOP with, okay, the usual perfect completeness and some constant soundness, where crucially the proof length and ideally even the prover time are linear in the computation, and the query complexity and also the verification time are polylogarithmic in the computation length, okay? So that you have linear size proofs that are verifiable in polylogarithmic time, okay? For any sort of time t computation specified by some machine, whether it is a Turing machine or a random access machine, okay? Now, this, to a first approximation, remains an open question to this day, but primarily for technical reasons, okay? There are, if you're not too careful, if you're not super paying attention to kind of, do we achieve this in full, we will kind of morally achieve something like it. We'll basically prove a large alphabet relaxation of the theorem that says that for every field that is large enough, like at least as large as a computation, and again, smooth, if you consider kind of non-deterministic computations that are kind of arithmetic over that field, and here, this is not a precise notion, I'll make it precise later, we'll basically achieve what we want just over a larger alphabet than the binary one, the natural one for these arithmetic computations. And here, the proof length will indeed be linear with a polylogarithmic running time. Here, the prover time will be superlinear, but again, we're not going to pay attention to prover times in this course, okay? The main point is that this is achieving linear proof length with polylogarithmic verification for some machine model computation, okay? And that is what we're going to prove today. Any questions so far? So just before we continue, like, is it clear sort of how a circuit is not an arbitrary circuit is not an example of a machine computation, right? So by the time you've read the circuit, you might as well have evaluated it on some witness, right? So there's nothing you can save in running time. In a machine, right, I gave you like the code of the machine, but the machine can run much longer than its description, right? And in fact, I would say most computations that you're familiar with have this flavor, right? So think of your computer. It processes a few billion instructions per second, right? But most programs will use a few megabytes or hundreds of megabytes of memory. And the program that you are running will maybe have, I don't know, like a few megabytes of code or something like that, right? So the time that these programs will be running will generally be much, much, much longer than the description like of the machine code that represents the program, okay? So these are the R machine computations. And if you think about Turing machines, it's like pretty extreme, right? A Turing machine has constant size description, and yet it is Turing complete, right? It can conduct any computation over it, right? So the growth of the computation is not in the description, it's like in, you know, the tape will kind of keep moving as a function of what the tape head wants, right? And there's a finite size automaton that controls the whole thing, right? So you have like a finite size description for something that can process computations of any input length, right? This is distinct from a circuit where somehow you can think about it as some sort of unrolled computation with no structure that has any a priori structure. It could just like random looking. And right now, somebody has a question about space. Right now, we're not paying any attention about the space of the space used by the computation. For all I know, it could be on the order of t. And if it's less than that, we won't pay any attention to that. Great. Okay. So, and by the way, why are we paying attention to the verifier running in sublinear time, like less than t? Because you want to delegate computations, right? These are computations that maybe some difficult big computation, you want the prover to do it, and the verifier should not only make a small number of queries to the proof, but also not do a large computation. And this type of statements are actually exactly the kind of statements that are used in the real world for things like roll-up architectures in Ethereum, where you have some small program that describes the roll-up state transition. And there is a large non-deterministic witness, which is the batch of transactions being processed in a roll-up batch, right? And you don't want the smart contract to verify a short proof in a long amount of time. You want the smart contract to verify a short proof in a short amount of time. Okay, so this paradigm of machine computations with sublinear verification is very useful in practice. And in fact, the IOPs that are used in practice are not very different from the ones that we'll see today. I mean, they're much more optimized, but they're morally kind of the same thing. Okay, so let's get started. So let's talk a little bit about machine computations, because we haven't seen them in this course so far. Informally, a machine is an automaton that can read write to some type of memory, right? And if by memory you mean tapes, then you get basically Turing machines, right? And if by memory you mean some random access memory, like can sort of specify an address and you fetch from that address without having to wait for the time to move to that address, then you're going to get kind of something called register machines, or also known as word RAM, right? This is basically pretty close to how we think of a computer, all right? Either way, these are both machines, okay? And so we're going to define languages that model machines that compute over finite fields, okay? So we're gonna have to consider some sort of arithmetic-like machine computations. So it will be easier to first kind of put aside memory for a moment and just talk about how just some sort of arithmetic automata. it would be just easier to focus on that first, okay? So there is no memory beyond the internal state. So consider that an automaton in this case will be defined by two parameters, k, which is, you can think about it as the state size or the number of registers, and some evaluation function e, which kind of evaluates the next state from the previous one, okay? So it maps k registers, k field elements, into new k field elements. Right? So a t-step computation looks as follows. You have some initial state, maybe all zeros or all ones or all fives, some standard initial state. And you apply the evaluation function, and the computation evolves time step after time step until you have done, say, t transitions, right? Here they are, first transition, second transition, blah, 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 until t transitions. So specifying the computation requires specifying this computation requires giving me the transition function that will cost you size of e, plus some time bound that tells me how many steps I want to take. And specifying the time bound is like t bits. So an integer t, which requires log t bits to represent, right? However, the specified computation involves t times size of e operations, which is exponentially more than that, right? So now I'm just trying to drive home the message that the computation length is much bigger than its description, right? Because if I'm telling you, take this transition function e, evolve it for t steps, for me to utter this description, it suffices me to kind of say size of e plus log t bits, right? Yet for you to conduct the computation, you have to perform the evaluation function once, twice, three times, t times in total, so it's e times t, right? So this is, the description is much smaller than the computation sort of size, right? But so far there's nothing like transcendental, I'm just kind of pointing out like rather obvious things. And so this is going to be our baseline for linear, right? So we're gonna want to aim for proof lengths that are this many field elements, okay? If we have like a proof length that is e times t field elements, then we call that linear because that's kind of the size of the computation. Of course, the more complex the transition function is, the more we have to take into account, right? So we do not expect to not pay for that in the proof length, okay? That kind of is like and it's an inherent parameter to the complexity of computation, just like the number of applications just like number t. And then we'll actually consider, we'll be interested in non-deterministic computations where E itself is allowed to make guesses, but we'll come back to that in a moment. Before we do that, however, hopefully it's clear what's the mental picture of machine computation. You can think about it as just a repeated circuit some number of times, right? Applied in a chain, right? Any questions about this? And again, the only reason why we're considering arithmetic computations is because we will be using arithmetic tools, okay? And while you can always take Boolean things and embed them into larger fields, you will have sort of superlinear overheads. So here I'm saying that we're going to achieve linear length for things that are already native to the field side, to the field that we're working with, okay? Just like it's exactly what happened for R1CS yesterday, where we were taking some R1CS instance of a particular field, and we were kind of building a linear proof length, so a linear size IOP for that field, okay?
Sorry, I'm a bit lost with the role of the machine here. Like this is a kind of computation we want to prove. And yeah,
so we want to prove statements of the form ST equals e to the t of f0, okay?
Yeah.
We want to prove statements of this form, okay? This is an automata computation, okay? Automata are just finite state machines with no memory, where so the whole state is just in the registers, right? So we're just performing some state transition t times, and there's some logic that represents how we evolve things.
Okay.
Question? Great. So now we're going to make it a little bit more precise. We're going to define a language that captures the statement we want to prove. Okay. So we're going to, these types of problems for machines are typically called bounded halting problems. Okay. So BH is the set of instances EZT, where E is a given transition function, Z is a computation input, and T is a time bound, for which there is an execution trace, okay, such that each step follows the transition function. So here we have it, that we are applying the transition function from the previous state and we obtain the next state, okay? And also the first n values of A1 are Z. So this is kind of like the public input, right? Similar to how we had a public input in R1CS yesterday. And the last value of A1 is 0, okay? So this is saying the computation accepted, all right? So I am kind of folding away the output. I don't want to talk about it right now. It will just complicate things later. So let's just say that somehow the output is handled already as part of Z. And we're just checking that the output of the computation is 0 at the first register, okay? So these are kind of the K registers as they travel through time. Here we're passing the T value of the K registers, and we obtain through the transition function the values of the next time value, the next value of each of the registers, right? And in general, an input may not fit in the number of registers, so I'm kind of striping it across time within the first register. And we're saying the first register is responsible for containing the input in the first n time steps of the computation, okay? Because I don't want to have to say that the input must fit, like, must be smaller than K, right? This is normal, right? If you think about a Turing machine that starts reading its input, it will read it over time, right? So this is like saying that the input is read into the first register in the first n time steps, okay? So that should be kind of familiar. And so now, so this, I think we can all agree, like, captures some sort of some notion of algebraic automaton. We're just going to massage this problem a little bit to make it more about satisfiability so that we can kind of then prove some things about it. So we are going to identify the integers 1 through t with a multiplicative subgroup that is generated by omega of size t. Why is that? Now remember that the verifier, we want the verifier to not have to think of anything of size t, because we want the verifier to run in time polylog t, right? So if I'm going to work with finite fields, I need to identify some domain in the field that has short description, okay? That can represent integers 1 through t, or like things of size t. So here it will be a natural choice is to just pick H to be a multiplicative subgroup that is generated by some element of order t, right? So that when I hold this element in my hand, it's as if I'm describing this t of size, this set of size t, but I don't have to like have it physically in my hand. It's just a description of the set, right? So representing H requires only log f bits. It's just one field element as opposed to like a bunch of field elements. Now we're interested in checking, not computing. So we translate the circuit E into quadratic equations, okay? With M equations and L auxiliary variables, all right? So how do we do it? Well, just Cook-Levin theorem, right? This is just some arithmetic circuit. I can just break it down into a bunch of quadratic equations, right? And let's just give it a name, P1 through Pn, okay? And I'm going to have some sort of k variables for the input, k variables for the output. That's 2k, and some number of intermediate variables. Overall, we have a total number of order of E variables total, okay, to describe kind of the satisfiability of this transition. All right. So there's nothing, we have already done this, I think, with Tom, when you've seen the linear PCP for quadratic equations. There's like a trivial NP reduction from circuit satisfiability to quadratic equations. You just kind of break down the circuit into gates and you have quadratic equations to describe it, okay? So there's a question, is K some space bound? No, I'm not assuming that N is at most K. that was kind of my point earlier. The size of the input is scattered through time. So you can imagine that this is the register 1 as it travels through time. This is register 2 as it travels through time, and up to register K as it travels through time. And we're saying that the input must be stored somewhere here in the first n time steps. Okay. So in particular, there is no relationship between K and N. Okay. But of course, whatever K is at most E, right? So great. So now we can actually say that an instance is in the bounded halting language if and only if there is an augmented execution trace, A1 through AK, and let's call these auxiliary registers, okay, B1 through BL, such that all of these equations are satisfied. So what am I going to pass in here as input? I'm going to pass as input the state of the current time, the state of the next time. But what is the next time? I'm going to take the current location, which is omega to the t, and by multiplying it by omega, I'm going to go to omega to the t plus 1. That's like the next time step in this total order inside this cyclic group H, right? And then I'm also going to provide the auxiliary variables needed for making this equation satisfied, right? These are kind of the auxiliary variables coming up from reducing a circuit to quadratic equations. And I want this to be enforced for every state transition. But of course, the last one I don't care about, because even if it wraps around, I don't care. And separately, I also want to make sure that this execution trace in the first so many time steps, it agrees with Z. And of course, the last time step, this one here, is 0. Okay? So what I've done is basically I've translated a question about automata to still a question about satisfiability, just like this mini system of quadratic equations repeated a bunch of times across a cyclic group, right? So we have this kind of cyclic group of size t. Each of these transitions, we think about it as a time step. We don't care about the final sort of transition back from the last element to 1, because we don't care about coming back. And at the end, I want A1 to be 0. Here, I want Z to appear in A1, right? And kind of in all of these transitions, I want E to be computed correctly. For E to be computed correctly, I just need to make these quadratic equations satisfied, right? So why are we going down to quadratic equations? Because we're about to, we want things to have like well-defined degrees. We want to be working with polynomials. We want to be working with sort of explicit things we can talk about, right? As this circuit, E may have some depth that if we think about it as a polynomial, will have high degree. So we don't want to think about it like that, right? So we want to kind of break it down into elementary gates, introduce auxiliary variables, so everything has bounded degree that we can understand, okay? So this is a kind of a should be fairly standard things given what we've done in this course so far and in the other course as well. Any further questions about, there's a question about why do we need auxiliary variables? Because when you translate a circuit with inputs into quadratic equations, you basically go inside and you take every plus and times gate and you give them names. This is going to be, I don't know, x17, x32, and you write a bunch of quadratic equations for each of the gates that relates kind of constrains all the variables, including inputs, outputs, and intermediate variables inside the circuit, okay? And before, we only had input variables and output variables, but then we also introduced these intermediate variables as well, okay? But how many variables there are? No more than the size of the circuit, okay? This is completely analogous to when you reduce, I don't know, Boolean circuit satisfiability to 3-sat, okay? You're kind of breaking up the circuit and introducing auxiliary variables to represent the computation of the circuit using 3-sat kind of formula, right? So, all right, your question? Any further questions about this slide? We're just basically trying to get to a form that we can write a proof system for, okay?
Yeah, I did not really understand. Why do we scatter the input over time and not over space? Why don't we load it into the first positions of all the registers?
Good question, because I don't want to assume that a k is greater than n. N in general could be something pretty large, but the number of registers may be pretty small. So I don't want to have to assume that. And again, this is sort of, and that's generally how programs work, right? So if you have a program, like, I don't know, a computer has, I don't know, 32, 64 registers or thereabouts, like it's a small number, right? So when you provide an input to a program, it doesn't just appear in all registers. There's no space there. It's just over the first few time steps, the program will read the input, right? There's some sort of kind of preamble in the program that involves reading the input and doing something about it, right? Maybe it reads it into memory. Now, in this case, of course, it's a bounded space computation, so it cannot really do too much with it. But either way, kind of the right way to kind of think about inputs is as read through time, right? That's how programs usually work, right? There's a question, how do we know that H exists? Well, we make it exist in a sense that we'll consider a field where, this is true, okay? And we don't need this to be like exactly that size. We just need to be something of similar size. Like if it had been 100 times t, that's fine. We just have a bunch of unused steps at the end. It just doesn't need to be like enormous, right? We just need the ability to kind of travel along a large enough subgroup. Okay, we don't need about wrapping back like within like a small thing.
Yeah. Sorry. Alessandro, can you say again about this like reading input thing? So like from how we describe this system of equations, it seems like we can just by running a computation kind of restore, for example, this first index just by knowing which indices do we have like from the start, right? So it means that the complexity of this word, so that like in an arbitrary program, this input like it's bigger than the program, right? But basically it can be anything, like modulo some constraints. But here, if we start from some like initial configurations, then we just run this computation for n steps, and then whatever's coming up in the first register is our input. But then it means that the complexity of this input is not that big. It can be anything, right? Or I'm missing something.
It's just a parameter, like it's n, right? So we are, the input is whatever it is, right? So maybe I didn't understand the question, in the sense that I want to think of the input as an independent parameter from k and t, okay? So, and that's typically what happens, right? You fix a machine, that's now you fixed it, right? Now you pick the input size and the running time, right?
No, but my question is like, so we on one hand, we consider z to be an independent parameter, but on the other hand, we consider z to be like whatever appears in the first index during the first n rounds, right? But those first n rounds, they are like defined by how do we start, from which rounds do we start, and then we evolve it.
Yeah, but we are given the input z, like so, like. Maybe I still don't understand the question. I'm sorry. Oh. Like the input is part of is the description of the problem, right? It's part of the description of the problem. We just need to talk about how the machine accesses it, and we're just saying that it accesses it. Like the machine knows that it will find the input in the first n steps of the computation, right? Maybe your concern is about how does the machine know that the input finished, maybe, right? And that's like more of a syntactic thing, right? You can encode an ending into your inputs, right? That will tell the machine that the input has finished, right? But that's
no. That's not what I was talking. Okay, let me rephrase. I don't understand from which configuration do we start our. So to start the computation, we have to specify the indices.
You mean like the S0 from before? You mean this one?
Yeah.
Okay. Yeah. Here I just like made it go away in the sense that it's not really necessary to have it around. Here I'm saying it starts from whatever it is. Like it's really it's really like not, you can put it if it's convenient, but it's not really necessary. I'm just trying to kind of pick a simple enough problem. Otherwise, I would need to put another kind of sort of condition here that says A1 through, or maybe A2 through AK at omega to the 0 is, I don't know, 0 or something, right? That is something you could write. If that would be like this, the beginning configuration of a machine, regardless of the input, right? But I'm throwing it out, and we don't even need to talk about it, right? So
I think that the point of confusion is that in point 1, we require that A1 is computed by E. And I think we should relax that A2 and next are computed by E, because A1
is computed by E, point 1.
Yeah, A1 is on the right-hand side.
Yeah.
You have A1 T plus 1, and this includes this purple part, which is, we think of it as an input. And now it is computed.
But if it's still fine. It's not really computed. It's okay, fine. So maybe would have been so it's when we have existential quantifiers, computations are like relative anyways. So I'm saying that exists, right? So here you can imagine E doesn't even, maybe it doesn't do anything with this one. Like it doesn't write anything here beyond sort of a oh, I see.
So E is not a function, it's a relation on the previous and the next stage. Right?
I agree. So maybe here would be like better to write this one, comma, that one equals true. Okay. So that's really what I wanted to write. Okay. So, yes, good point. So let me just put a note here. So the challenge of talking about machines is that ultimately, in the end, we always end up talking about non-deterministic problems because that's the easiest problems to talk about anyhow. But to get some intuition that there is a computation that you could have run, like still want to talk about the transition function first, just to kind of, but still, yeah, I agree that right now I cannot quite express it like that. So, so I'll fix the slides. Good, all right, good catch. And so there's a question by Wilfred. The input is fixed. It's not fixed by that one. It's contained by that one. We are forcing the first n time steps of the first registers to be z. Okay. All right. So, okay. Any further questions? Great. Okay, so now we want to construct an IOP of linear size for this problem. Okay. There is a question of what should M be? The number of equations, it is, we can definitely bound it by the size of the transition function because we're going to pull out one equation per gate, right? That's how the reduction works. Whenever you go from some circuit to some set of equations, like, and ditto for the number of auxiliary variables, because you're going to create an auxiliary variable per gate inside the circuit. Great. All right. So let's. So we have one problem that we need to solve, which is we're going to need to ensure that the first register, for example, agrees with the input on a certain subdomain. Okay. So let's just make sure that we know how to do this particular subproblem. Okay. So let's say the verifier has local access to some function and wants to check whether its interpolation over some domain agrees a given target function. For example, all zeros or the input that we want. And we're actually going to use this target and subdomain into two regimes, for the input and for something else. Okay. So, but actually we've seen this before, right? We have, like, if I want to make sure that f hat agrees with z over h, it's enough for me to show that okay, what we've seen before is when z is all zeros, we've seen that f hat vanishes on h if and only if there is a quotient polynomial, so that I can write, no, just a second, here there's a typo. Agrees with z on h, if and only if, let me put a note, also fix this. agrees with z on h if and only if there is a quotient polynomial, so that when you subtract the z hat from f hat, you're going to get h hat times the vanishing polynomial, right? We have seen this already, I think, twice. Once in the linear PCP for R1CS, bundling together kind of all the equations into one check, right? And you probably have seen this again in one of the worksheets in one of the alternative ways of doing zero and subcube test. Okay, so you've seen kind of similar things before. So that means that I can just create a pretty simple IOP that says the prover will compute h hat to be f hat minus z hat divided by vh to obtain the quotient polynomial. We'll send it its evaluation, and the verifier will test that the quotient polynomial has the correct degree, and then it will sample a random point over the domain and check the identity test that it should have satisfied, right? And if indeed f hat on h agrees with z, then this quotient polynomial will have the right degree and satisfy the right equation, so everything will pass for every choice of gamma. If f hat does not agree with z on h, then regardless what h sends, we have two cases. Either the prover sends something that is far, in which case the verifier will accept with small probability because we're running a lottery test, right? Or the prover sends something that is close to some polynomial h hat of the right degree, but because this holds, this polynomial identity cannot hold. So the verifier will accept with probability at most degree over the domain plus delta, because the verifier is querying h, which is delta noisy at one random point. Here it is. And if f was also noisy, then you would have another delta here, right? But right now we're kind of not considering that. Is it clear? This is like a pretty simple test. There's a question about why does h have a hat? So hats I've been using in the last few lectures to denote things that are polynomials. Okay, so for example, here I'm taking the interpolation of f over the whole field, the interpolation of z also over the whole field, divided by vh, and I get a polynomial, right? Then when I evaluate it and I send it as an evaluation table, then I write it without a hat, but because that's its evaluation. Okay. So yeah, so hopefully, great. So f will have a degree at most d. So I should probably clarify this is degree of f is at most d. And z hat, anyways, is something that we imagine as not having large degree that is dominated by d. Anyhow, good question. There's a question about how is h sent. No, h has size L, right? H has size L because that's what it is. It's a univariate function over L, so it consists of size of L field elements. Remember, we are working with univariate polynomials, and I just send it, right? So, and L, generally speaking, is something that is going to be linear in our problem size. So think about it, 10 times the problem size, 100 times the problem size, something like that, right? So think of L as maybe 10 to the t or something. Z was in not even L to the n, but in F to the n, okay? But that's fine, right? I mean, you should think about that there is F is something big, that's over L. There is maybe some small domain H here, and Z is defined over that, right? Degree, and F maybe will have some degree that is roughly like maybe D somewhere here, right? So, and you should think of N as, much, much smaller than D, but it only has to be at most D. We are not assuming anything else. So Z hat is going to have degree at most N, right? Because you're interpolating just here, right? And that's it. It's just a polynomial in one variable of degree at most N. All right, great, good questions. Any further questions about the protocol? This is a pretty simple protocol given other things that we've seen. Right, So now, crucially here, something that we did not really pay much attention in the past is we want to say, what is the time complexity of the verifier, right? Because we want the verifier not to pain in the whole computation size. So, and for now, we're going to ignore what happens with this one because that's the low degree test and we're kind of factoring it out for now. But we know that Fry is going to be fine. If you remember, Fry is a low degree test where the verifier not only makes a logarithmic number of queries, but also the verifier, in terms of running time, makes a logarithmic amount of field operations, okay? And of course, this assumes that the domain L is smooth, right, of size 2 to the something, right? But okay, so in some sense, this part is fine, right? It's a kind of a small verification. But let's look at the other part, this part here, right? If Z is not 0, then we're going to have to evaluate VH at gamma and Z hat at gamma. All of this can be done in poly H because, well, whatever Z is has size H, and so we can do it in poly H. Okay? So this is, for example, when we have an explicit input over some small domain, and it's okay to pay in time there is polynomial explicit input. Another regime of parameters is when Z is actually the all zero string, and we're thinking of H as enormous, okay? Like size the computation. In this case, we need to evaluate VH at gamma, but fortunately, but in general, this would take poly H, but because H is a subgroup, we can do it in polylog H. And the reason is that if H is a multiplicative subgroup, then the vanishing polynomial just looks like a very simple polynomial. It's x to the h minus 1. Okay, so we're using the fact that the vanishing polynomials of subgroups are somehow ultra sparse and they can be evaluated very, very fast. Okay, so not only when I have a multiplicative subgroup, I can describe the set by just having in my hand the generator. Moreover, if I want to evaluate the vanishing polynomial for that set at any point in the field, I can do it in polylogarithmic time because the vanishing polynomial has the super special structure. In general, that need not be the case, right? Because a vanishing polynomial of some set, what am I doing? Okay, everything disappeared. I don't know why. In general, if you have some vanishing polynomial of a set S, the polynomial will look like this, right? And evaluating it will cost you poly in S, right? But this is a general form. In the particular case, when S is a subgroup H, then kind of all the terms disappear and you're only left with x to the h minus 1, all right? There's an easy thing to check. It has to do with the fact that everything in a multiplicative subgroup is a root of unity, and therefore it must satisfy this characteristic polynomial for roots of unity, okay? So that's why, right? So, and so this is saying that this target and subdomain testing, when I have a particular target, I'm going to have to pay polynomially in that target. But if I have a very special target, 0, then actually I don't have to pay in the size of the domain that I need to check. I only need to pay in polylog that, okay? And we'll be using this target and subdomain testing twice, once for something small and non-zero, and another time for something enormous and 0, okay? Roughly speaking, it corresponds to the public input, the small part, and the huge one is like basically checking all the quadratic equations across all time steps, okay? That's roughly where we'll be using this. So, but we'll see that in the next slide. Any questions about, how does the target and subdomain testing work? And of course, I hope the name makes sense. We have a target on a subdomain that we want to test, right? So that's why we're calling it like that. Just pause for a moment and make sure that things are clear. Okay, I don't see other questions, so let's continue. So now we go back to our problem, which was this algebraic automata, and we're going to write down an IOP to check them. Okay, and our goal will be to have, remember, linear proof length and polylogarithmic verification time. All right. So the verifier and the prover are both given the description of an automaton computation. So the transition function, the public input, the time bound. So they both receive it. And of course, remember that the description of the computation is small. So by now, the verifier reading in full this one, it's okay. It's size of E plus log T, right? Plus N, of course, right? Additionally, the prover is also given, say, the augmented execution trace, A, that certifies that this one is inside the language. The first thing that the prover is going to do is going to run on the computation trace to augment it with auxiliary variables by basically seeing what happens inside the circuit every time step. This is going to give you this kind of auxiliary registers through time. Then it's going to low degree extend and evaluate on L each of the registers. Okay, and it's going to get some function F1. So F1 is the low degree extension of register 1. F2 is the low degree extension of registers 2. And so on and so forth. All of them are evaluated over L. Okay. Then it is also going to do the same for these auxiliary registers B. Okay, it's going to extend them and evaluate them over L. Then we're going to compute this quotient polynomial. And you're going to, these are based, this type of rational, they're called rational constraints, are extremely common in basically arithmetizing machine computations. What are we saying here? Here we're saying, let's consider the polynomial that you obtain by plugging in into equation J, like the Jth equation, okay? The polynomials corresponding to the low degree extension, to interpolating the K registers, the L auxiliary registers, and then also the next step of the K registers. How do I express the next step? I put an omega in front, right, to kind of go to the next field element. And here I want to basically create, I'm computing a quotient polynomial, not quite on the whole set, right? Because here I'm saying, let's check this equation at x and omega x, x omega x, and I want to do it for everything on H, right? But I also have to exclude the last point in X. I have to exclude the last point because I don't want to wrap around, right? We have T time steps, not T plus 1 time steps to check, right? So let me just draw it here. Here we have our cyclic group, right, of size T. We start at 1, omega, blah, 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 right, up to omega T minus 1, right? So omega squared, right? And each of these for us is a transition. Now, we need to exclude the final transition because we're not going to enforce that the last state transitions into the first state, right? That's not what we want. So we consider the vanishing polynomial, but we divide out one of those points because we don't want to step out of this last one onto the first one, okay? And similarly, I will also do a target on subdomain test, which is this one, on Z hat. I'm going to make sure that A1 hat stores on this small domain H input Z hat. Okay? Okay, someone is asking, why do we have the B's? When we translate an arithmetic circuit into equations, we obtain auxiliary variables, okay? At every time step. So those are the auxiliary variables to evaluate the circuit, step 1, step 2, step 3, and so on and so forth. And I'm going to provide them because we need them to evaluate the quadratic equations that are obtained from the circuit. Okay? Great, good question. So here I compute the quotient polynomials to prove that the equations hold everywhere for all its transitions and that the first register agrees with Z on the first kind of so many elements. And also, I'm going to say that the first register is 0. Okay, so you can think about it as -0 is 0 at the last step, right? This one is saying that omega to the T minus 1 is a root of A1 hat, right? This is what it's saying. Right? So all of these are kind of witnesses that certain polynomial identities hold, and I send them over together with all the log extensions. So I send the log extensions of the registers, the auxiliary registers, these quotient polynomials for each of them equations, and then the quotient polynomials for agreeing with the input and outputting 0 at the end in the first register. And they're all gone, right? And the verifier, what is it going to do? It's going to test that each of the received functions have the appropriate degree, okay, using Fry. And then it will check each of these polynomial equations at a random point. So here is checking this equation, here is checking this equation, and here is checking this equation. And of course, just like in other lectures, we need L to be disjoint from H. Otherwise, we're going to run into some trouble dividing here. Okay? And kind of here, oopsie, I mean, maybe before I'm gonna go there, let me, so we're about to do completeness and soundness. Okay, it's gonna be rather straightforward. Is it syntactically clear what we're doing here? You can think about it essentially that we are taking the whole computation and thinking about it one register at a time, extending each one of them. So this is basically sending, this is the logic extension of the whole computation, and we're sending it. And each of these are certificates for 3 different properties. This one certifies that the M transitions for each time step were conducted correctly. This one certifies that the first register agrees with Z on the first N time steps, and this one certifies that the first register at the last time step is 0. And these are all the conditions that we wanted to make sure hold for the automaton computation. Okay. Let me just pause for a moment. That kind of
So in this last check, we just check the evaluation of H0 hat at single point, and we don't want to do this by a single query at this point because this polynomial can be noisy, right?
Exactly. Yes, we cannot afford. So it's a great question. So in principle, if if F1 had been sort of a perfect polynomial, and we're just wondering, I wonder what is the value of F1 at omega to the t minus 1, we would just square it, right? But there are 2 problems with this. First, it might be noisy. Second, and in some sense more fundamentally, L is disjoint from H, okay? And omega to the t minus 1 is on H, but we're given F1 over L. So we don't even see it there. And so that's why we write a rational constraint to enforce it. We're basically saying, prove to me that the polynomial that interpolates F1 has a root at omega to the t minus 1. Okay? And the way you do it is you show me the quotient polynomial so I can then check that this is the case. Okay? And writing these types of rational constraints is actually pretty fun. You can take, I think in tomorrow's worksheet, you will be writing rational constraints, I think, for maybe computing for an automaton that computes Fibonacci sequence in 2 different ways, using 1 register or 2 registers, and sort of basically going back in time to fetch the previous value from 2 registers, or going back in time twice from 2 registers into the different time steps, right? Because Fibonacci involves 3 variables at once. There's a question, why do we need L to be disjoint from H? Is because we need to do these divisions, okay? And we wouldn't be able otherwise to evaluate things over L if we had 0 over 0, okay? Or something over 0. Right, so here we're right, VH will vanish everywhere on H. And if H is in L, then we wouldn't be able to evaluate things here because we'll be having something divided by 0. Good question. And also another point is that it's becoming less and less so, but until about 1 or 2 years ago, most applications of this type of things in the real world, you would actually have programmers like directly writing these things. It was, you know, to kind of represent computations of interest. You just think of a machine, and then you basically write equations that are going to kind of enforce that machine's progress. These days, you have a bit more usable abstraction barriers. Essentially, what people have done in industry is to develop highly optimized kind of rational constraints for a universal machine that exposes some simple machine code. And so you kind of optimize once and for all some universal machine, and then you program things onto that universal machine without having to worry about sort of these sort of rational constraints. All right, so let's move on. Let's talk about completeness. So suppose that you have an execution trace that is valid, that, you know, makes all the transitions happen. Well, here the prover can evaluate the transition function at every time step to obtain the correct auxiliary registers so that the m quadratic equations are satisfied at every time step. So the prover can really find each of these polynomials. Also, we are given that A1 agrees with Z. So again, HZ and HZ can be found, and 0 is on the last entry. So again, H0 can be found. And here, like, I want to sort of talk about syntactically what's happening, right? So the proof length, what is it? It's K plus L plus M times L. Okay, but remember, L was like linear in H. Think about it like 10 times that. And K and L and M, they were all at most E. So now we have a proof length that is E times E T field elements, which is linear in the computation size. That's great. So we have a linear size proof. The query complexity is going to be, because of running Fry, logarithmic in the domain, okay? And how many queries are we making? We're making as many queries as there are oracles here. So that's E log T, all right? The prover time, we're not really going over it, but it's basically doing polynomial arithmetic over things of size L. So with FFTs, it can be done in L log L. So you think about it as E times T times log T. So something pretty close to linear. Now, crucially, the verifier time, for running Fry, there is, of course, log L. That's great. But then, like, the largest thing here, which is to evaluate, to check something, not the largest thing, but sort of all the things here are pretty easy to compute. We're paying in M, that's fine, but we're not paying anything that is linear in T, right? Because T appears as an exponent and we're paying log T in that, right? So overall, we pay something that is K plus L plus M times log L, plus something that depends on Z, right? Because this Z hat will cost you poly N. So we're paying E log T, which is exponentially less than that, plus something that grows with explicit input, right? That we cannot avoid. Oopsie. Any questions about any of these complexity metrics? Again, the key point here is that we've designed a protocol where the amount of field elements that we send is a constant times the number of field elements that are contained in the computation transcript without any proving, right? So it's a linear proof length. And the verifier never has to pay something that is linear in T, okay? So it's kind of polylogarithmic in T. Of course, it will have to pay for things that it receives explicitly, like the size of E and the size of Z, right? So it will pay size of E and size of Z.
How verifier evaluates this polynomial in log L time? He uses some form of Fourier transform, or?
Wait, sorry, are we talking about the prover or the verifier?
The prover.
Oh, this L log L comes from FFT, using FFTs, yes. So here, this is a polynomial division, and, you know, how do you do polynomial divisions? You kind of evaluate, divide, and interpolate, right? And all of this kind of change of basis from kind of coefficient basis to evaluation basis can be done with FFTs. In general, FFTs are going to be L log L, log L. But if you pick your domain nicely, for example, to be kind of FFT friendly, then you can do it in L log L. And we do have it FFT friendly because anyways, we're running Fry later. And so we want L to be smooth, like 2 to the something. And so once you have 2 to the something, you can run the standard radix 2 FFT.
And what about the prover space? he's gonna need to store the entire program.
Yeah, and it's a pain in the neck. So in fact, in practice, the L log L is not really a big deal. What is much more a limiting factor is the fact that you have to, in order to run the FFT, you have to kind of allocate an enormous amount of memory, size of L, right? So that you can do the in-place FFT with this like huge array of size L, right? And so if you think of maybe a computations of consisting, I don't know, of 1 billion steps, right? Kind of running the prover will already be maybe like a computation that will use maybe the largest machine on some cloud provider with maybe more than 200 gigabytes of memory. So it's pretty annoying. And so, you know, in the real world, you start breaking this computation down, and you do some sort of engineering about doing FFT in pieces, and you can kind of mitigate some of these issues. But let's put it like this. One of the maybe very exciting open questions is how to achieve very good prover time and good space prover. I mean, good kind of prover space. So you don't want to have to use FFTs on such large objects, okay? And in the pure IOP model, we don't really have an answer. We have some partial answers in other models, like with discrete logs and things like that. You can get something a bit better, but they're not that practical at this point. Any other questions on complexity metrics?
Okay, so I don't get why we need FFT to make this polynomial division, because these polynomials are non-zero on L, right? What we divide by is non-zero on L. So we can just divide numbers because we want to generate this evaluation tables on L, right? We need FFT to interpolate, but
yeah. So even just going from let me just try. So yeah, even going from AI to AI hat, right? This interpolation, that's already an FFT.
Okay.
So before even you get to the division, if all you wanted to do was to go from AI to AI hat to AI hat to L, right? This is basically the logic extension. You have an inverse FFT and then a forward FFT right there, even before you divide anything. Okay. Good question. All right, so Bagdan has a question about soundness, but we have soundness in the next page. So we'll talk about soundness next page. Any further questions on completeness or complexity measures? Great. So soundness. Suppose that the instance is not in a language. So there are two cases. Either one of the functions that the prover sent is far from the Reed-Solomon code, in which case, well, you know, what does it mean? It means either one of the functions for the registers is far, or one of the functions for the auxiliary register is far, or one of the kind of witness functions is far, right? So one of these things, and they all have potentially slightly different degrees, right? And, you know, I kind of reported them here. That's why I didn't really kind of put them here, because anyways were going to happen here. If any of these conditions holds, then the verifier accepts a small probability, because that's the guarantee of the test, right? So suppose that all of those functions are close to unique polynomials that I'm going to denote by hat, okay? So now we have some, these are noisy, but they're pretty close to the corresponding polynomials with the right degree. So then we must have one of several cases. Either one of these equations is not satisfied, okay? Either the pjth equation here for some j, or the equation that corresponds to the target and subdomain, or the equation that corresponds to the value on the last step, okay? Whichever of these, in any case, we have some consistency check. For example, here we'll accept the probability at most this much. With this one, it would be at most this much. With this one, it would be at most this much. By the way, notice here that we have a kind of a large thing in front, is because we're querying a bunch of things, but as it was mentioned in some past lecture, it doesn't really have to be there, because you can make sure with Fry that all the errors are correlated. And so as long as you query everything on the same location, you're going to have something more like a small constant times delta, all right, like 2 times delta. But again, this is the type of analysis that I'm writing explicitly, but you should at this point be able to reproduce by yourself, maybe, I don't know if in your sleep, but almost, because all these analyses, they all look the same, right? Either something that was sent is far, or everything that is sent is close. If everything that is sent is close, they're unique closest polynomials. And one of the conditions that you're testing for is violated. And so go and see what is the degree of the polynomiality test that was run on that one, the end, okay? So all the analysis that we've done are of this character. So yeah, so that was a comment. There are many ways to make this less than 1. And I even wrote them, but I don't want to go over them right now. So this is like for whoever is interested, how to, sort of not have a dependence on number of registers times delta. But I hope, Bogdan, I answered your question, that in particular, there's no dependence on t because kind of the t is folded into this equation itself, right? So this is basically saying the jth equation is satisfied at every time step, and that this whole thing is summarized by this rational constraint. Great. Any further questions on soundness?
Yeah, if we have multiple low degree Frey tests, can we somehow batch them together like we did?
Yeah. So, and I'm not saying it here, but in practice, you would never run a bunch of different Freys. You will just line up all the things to be tested, shift if needed, if there are differences in degrees that you're looking for, and take a random linear combination and run Frey on that. One advantage when you do it is that also that the analysis will tell you that the errors are correlated, so that you don't have to deal with sort of querying many things at the same location. You don't have to pay for that. You'll be querying sort of all things at a small number of locations, and you will pay a much less sort of overhead on that. Right. So in this case, for example, we are querying all the Fs and all the Gs at X, right? And the only things that are queried at 2 locations are F, because it's at something, and that's something times omega, right? So you have 2 locations for F. But otherwise, everything else is queried at one point, right? And you can even reuse things. Like, for example, notice here how we are reusing the value of F1 here and here. It's like literally the same point. That's fine because we're not relying on the fact that they are independent. It's okay to have them completely correlated. And it's also reused here. Any other questions? All right, to a first approximation, this is basically a protocol that is used in practice in a few places. It's used for roll-ups, okay? Roll-up architectures. Now there's something though that's missing here. Like so far, we were talking about automata. And so we only have 20 minutes. And we're not gonna go through the whole thing about machines, but we have an example for it. We have an exercise for it in the worksheet where you work out sort of the missing piece that we're not doing today. So when we go to automata to machines, the main thing that is missing is that we had to have memory somewhere in a machine. So the picture you should have in mind is more like this. Every time you transition from a state to the next, the transition is allowed to make a memory access. So maybe it reads something and it receives back the answer, or maybe to write something at an address and then the memory says, okay, I have received the command. And of course, you can dream up all kinds of architectures where every time step you have like 5 writes and 3 reads, right? So let's consider something very simple where at every time step, either you read or you write, okay? So that's how the machine works, okay? And I'm not considering tapes. I'm even considering a situation where you have addressable memory. So this is a machine, all right? And so if we extend this state with the memory, we will end up with t-squared variables that is beyond linear, right? So we cannot just say, okay, let's just take the machine and reduce it to an automaton by extending basically this state by the whole memory. Now we're carrying the whole memory at every time step, and we'll get a big square that is t by t, right? That is not a good way to handle memory, okay? It will make it impossible for us to achieve a linear size proof if we just kind of already create a quadratic blowup at the very beginning. So the challenge here is that memory is kind of not, it's kind of like a runtime thing, right? Like depending how the computation goes, you can touch this place of memory or this other place of memory, and they could be all very different, right? And we have to somehow capture this using some fixed constraints that the verifier will check, right? Now, and there's a key observation that we don't actually need to maintain memory at all. It suffices to put in place a set of invariants such that they imply that memory was behaving correctly. And so I like to think about this as what you wrote is what you read, okay? Or what you read after, right? So that's the only thing that we care about memory, right? So if you wrote there and you read, you're supposed to get what you wrote the last time, the end, right? So, and of course, if you read it again, you're supposed to get the same value. This is the invariant of memory. It doesn't really matter what is in memory, just this invariant is what matters. And so the trick here is to consider two traces of computation, one ordered by time, and other one that we're going to call time trace, and another one called memory trace that is ordered by memory. What does it mean? It is ordered by address and then by time step of access, okay? So you can think about it as like this. So here's an example of a memory trace. You see that it is ordered by address. So here are all the accesses to address 2, then all the accesses to address 5, all the accesses to address 7. Why is there nothing on 3? Because 3 was never accessed, okay? And then it's ordered by time, meaning that if within the accesses to address 2, I order according to time. And you have, either a read or a write, and whether it is a value that is read or written, right? So here's a memory trace, and it turns out that the invariant, what you wrote is what you read, can be very easily expressed if you're given a memory trace in this order, right? Because the trace is correct if and only if for every 2 adjacent pairs of operation, address, time, and value, operation prime, address prime, time prime, and value prime, the following holds. If you're looking at the same address and the time increases, so then you want to make sure so if you're looking at the same address, then it must be that the time increases. And moreover, it must be that if you are reading, then you're reading the same value, okay, as the previous one. If the address is different, then you need to make sure the address goes up, okay? And that's it, really. It's a very simple thing, and you can just check them side by side. So, like memory is difficult to check if things appear all over the place in your time trace, but there is a way to reorder the time trace into memory trace so that memory checking is some trivial check that is a pairwise check, right? From from 1 to 2, then 2 to 3, 3 to 4, 4 to 5, right? So is this clear, right? So I'm not saying yet how I reorder the trace. I'm just saying if the trace is reordered, then we can do these very simple checks, right? There's a question about, do we need a write check? It is handled here already, right? Because when you write, you are overwriting whatever is there. So it doesn't matter what was there. What matters is when you read after some operation, whether it's a write or a read, okay? So the write check is doesn't matter, right? To put it differently, if you write and never read again, it doesn't matter what you did, right? So it's already handled here, right? So the previous operation could have been a write or a read. It doesn't matter. Whatever it was, you must read the same value if the next operation is a read. Good question. Any further questions? All right. So now we have made this observation. We're gonna notice that it suffices, like essentially. So there's something out of order here. All right. We can basically write the computation of an algebraic machine as basically an algebraic automaton plus the help of our permutation. on the time trace. So let's try to write it. So we have a way to transform some algebraic machine into a list of quadratic equations such that it is a valid machine computation if and only if there is an augmented execution trace as well as a permutation of it, such that we have some number of equations that look at this time step, the next time step. So you can think about this as being for the time trace. And then you're comparing this time step and whatever time step is set by the permutation. And this is the suggestion by the permutation of saying what is the next one in memory. Okay? And so the PJs collectively will be responsible for implementing whatever simple logic there was on the memory checks between these two, right? And that's it. So basically by augmenting the previous problem with a permutation and giving the permuted inputs, we can express machine computations without any blowup, all right? Again, we have one set of equations responsible for the time transition of applying E from the current time step to the next one, so from omega t to the omega t plus 1, as well as implementing whatever simple logic, which we can of course write as gates, from the current step to the next memory step. What is the next memory step? I don't know. It depends on the computation. Let's ask the prover to give us a permutation for that. Okay, so for some permutation. All right. So now, okay, this is basically what I said. The completeness is that you choose the permutation to be the correct reordering of the trace by address and time, so the memory checks pass. And soundness is that for any permutation, either some memory check will fail or the read-write operations are all correct, so the transition function is fed the correct values, right? So is it clear that because of thinking of a trace and a permuted trace, that this one will make sure is in the correct memory order, we can have this reduction? So is it clear that, so yes, pi must be a permutation. Multiple time steps can point to the same time step. No, it's like really a permutation, right? Because down here, each of these happens in one and only one time step. For example, see here, these are all different time steps. We only have one access memory per time step. So this really is a permutation. So in every transition, there is a single memory step, right? So when I sort of reorder them by memory in this memory order, that is a permutation. Okay. I hope that answers the question, Tal. Great. So we have this new problem that we want to probabilistically check. And we're basically done in a sense that the way we're going to construct an IOP for algebraic machines is that we just basically use the same one for algebraic automata, but we have to design a new subroutine, which is an IOP protocol for a permutation check, right? So we're going to ask the prover to give us the permuted trace, and we're going to check that there is a permutation that explains it, right? So we're considered a setting where the verifier has oracle access to F and G, and wishes to check that there is a permutation such that explains G in terms of F hat, all right? So that to the PJs, we're going to give F, F shifted, and G. And separately, a different subroutine will ensure that G is related to F by some permutation, okay? So a common technique in the PCB literature relies on routing networks. It's a very beautiful technique, but this will give you size T log T, all right? So routing networks are in particular permutation networks, and combinatorially, they must have size T log T. This is similar to why sorting algorithms, must have T log T comparisons. But here we are interested in linear proof size, and we're going to use interaction to achieve proof length order of T. And this kind of points to the worksheet that you're going to see tomorrow. The main idea is that we're going to base the protocol on the fact that this equation this equation here, is equivalent to asking to whether these two sets are equal as multisets. All right, so this being a permutation of that is the same as saying these collectively are the same multiset. All right, so yeah, and so and it's on its own, that is the same as saying that they are the same roots of the same univariate polynomial. Okay, and this observation will let you in the worksheet design a cute subroutine for implementing this via permutation check. Okay, so any questions about this slide? Oh, what is a multiset? Sorry, that is a set with repetition. Okay, so if you have the same element appearing multiple times, then it appears multiple times as opposed to one time. That's a multiset. All right, so I'm not going to show the permutation check here. Okay, it's a very nice exercise in writing rational constraints. At a very high level, what you're going to do is that you can write a teeny tiny automaton that basically computes this identity test at a random point, all right, across time, all right? So you can write a teeny tiny automaton that computes this. So in some sense, the way you handle machines, you use interaction to reduce them to an augmented automaton. And then you run the previous protocol on the augmented automaton. That's roughly the way you think about handling machines with linear proof size. And actually, this is indeed how it's done in practice. In practice, you will have an IOP for machines that relies on this kind of permutation check to have memory, okay? And memory is actually quite important because, for instance, in practice, if you want to have things like recursion calls or having a function stack, right? You're going to need to have some memory to store things and fetch them later. And it will make it much easier to write programs, machine programs, that can then be composed in interesting ways to realize whatever computation you had in mind, right? So, and there's been like a lot of very nice work, engineering work, highly non-trivial, on basically coming up with basically virtual algebraic machines that are sort of highly efficient and expose some sort of reduced instruction set architecture on which you can express pretty complex things. And underneath, they're using sort of highly efficient sort of memory subroutines for checking permutations. Okay. I think this is a good place for me to stop and take more questions. Oh, I wanted to first maybe preview. So tomorrow is the last lecture. We will talk about, we've talked a lot about what IOPs can do, and we'll talk a little bit about what IOPs seem unable to do. Okay, we'll talk about proving limitations on how sound an IOP can be. All right, and because generally speaking, so far we've talked about constant soundness error, but ideally for real world applications, you actually really want things to have very small soundness error, and you want to try to understand what is the ultimate trade-off between a given number of queries and the soundness error you can achieve for that, right? And ideally you want to be in real world as close as possible to that, right? Instead, Tom will talk about, he will also shift gears and talk about applications, so delegation of computation and hardness of approximation. Both will be, I would say, generally fairly more lightweight lectures, and so that will kind of conclude things. And tomorrow at the recitation, you will have worksheets about this permutation check and writing rational constraints for Fibonacci. I think it's a really fun worksheet. I definitely encourage people to try it out. These rational constraints look awkward, but when you get the hang of it, it's actually pretty interesting to write them for sort of properties of interest. All right, I'm going to stop the recording and take questions.